we have this alternative form of the definition of the derivative, and this is on your formula sheet. You must know it. You just have to know this thing. One of the things that this formula is going to allow us to do is going to allow us to test for differentiability. So because we're trying to find the derivative at a point, right, c is some point, some x value, this allows us to test from the left and the right and figure out if the derivative exists or not. And so we've learned this formula before, and we use it for the slope of the tangent line. And we talk about a couple of things. Derivatives are limits. They are limits. So for the derivative to exist at a point, the limit must exist at that point. And the derivative, which is just slope, from the left and the right must be equal. And so the way we say that in calculus is the limit as x goes to c from the right of f prime of x is equal to the limit as x goes to c from the left of f prime of x. And so this is how we would say it in calculus. And we're going to jump around here a little bit. So we're going to go past example 1a. We're going to not do 1b. And we're going to start in with 1c. And so what they want us to do is they want us to use the alternative form of the definition of the derivative to find the derivative at x equals c if it exists. So let's get started on that. And, you know, we love piecewise defined functions, so let's begin. The first thing that we need to do if we're trying to find the derivative of a piecewise function, and we're finding it at this point, this c, so this is our x value is equal to c, right? This is our domain change at changes at x equals 1. And since that's where we're trying to find if the derivative exists, we need to first make sure that this is continuous at x equals 1. And so we're just going to check real quick. We've learned the definition of continuity, we've learned definition of limits, we've learned IBTs, so now we're going to apply them. And so we know that for this thing to be continuous, my y values have to be the same. So let's just check with start with the top function. We get 1 squared plus 2. That's 3, so that looks good. And let's check our bottom function. We get 3 times 1. Ooh, my pen's going crazy. We get 3 times 1. That's equal to 3. So it is continuous at x equals 1, so that means we can continue. We're using the alternative form of the definition of the derivative, and so we're just going to jump right into that. I'm going to start coming from the left simply because that's on top. So we're going to use the alternative, so it's f prime of 1 is equal to the limit as x approaches 1. Now, for our limit, we're going to approach 1 from the left, and so that's our top function. So here's what we get. We get f of x, which is just x squared plus 2, and then we have minus, so we're plugging in this 1. So we have minus 1 squared plus 2. And this is all over x minus 1. We're going to clean this up and simplify as much as we can. And here's what we get. We get the limit as x goes to 1 from the left. So my x squared plus 2 minus, we have 1 squared plus 2, which is 3. So we're going to subtract 3. And that's all over x minus 1. We can combine like terms, and so we have the limit. We have the limit as x goes to 1 from the left of, this is going to be x squared minus 1 over x minus 1. We're going to jump down here, and we're going to simplify. We know we can factor the top. So we have the limit as x goes to 1 from the left of x minus 1 times x plus 1 all over x minus 1. My x minus 1's reduce, and we're left with the limit as x goes to 1 from the left of x plus 1. We substitute our value for 1 in for x. We're evaluating our limit, and this is 2. So here's what we ended up with. We ended up with, I'm going to write it right here. We ended up with f prime of 1, and we found the limit of this. So we're coming from the left, right? Correct? And we want to keep track of that. So we're coming from the left. We ended up with this as 2. So the rate of change when of this top function is 2 as it goes to 1. We're going to jump down and we're going to find, take the derivative of 3 of x, so as we're coming from the right. So we have f prime of 1 is equal to the limit as x approaches 1 from the right. So f of x is easy, that's just 3x, minus, so we're plugging in our 1, and we get 3 times 1, so we get 3, whoops, I'm going to open a set of parentheses here, we get 3 times 1, and that's all over x minus 1. So we know that 3 times 1 is 3. We have 3x minus 3 here. I'm going to factor 3 out as I rewrite this problem. So here's what we get. We have the limit as x goes to 1 from the right of 3 times x minus 1 over x minus 1. My x minus 1's reduce, and we're left with the limit as x goes to 1 from the right of 3, which is 3. So to rewrite this, what we ended up with, coming from the right-hand side, we ended up with, that green's terrible, let's go purple. We ended up with f prime of 1 is equal to 3. These two things are not the same. And so we need to do a little investigation. We kind of need to figure out what's going on, because so we need to take a look at this and try and kind of figure out what's going on here. And so here's how we're going to write this. We say the limit as x goes to c from the right of f prime of x is not equal to the limit as x goes to c from the left of f of x. And we can put this whole thing kind of in perspective here. Whoops. When we write out our final answer, here's what we're going to end up with. We end up with the limit, so the limit as x goes to 1 from the right of f prime of x is not equal to the limit as x goes to 1 from the left of f prime of x. Therefore, f prime of 1 does not exist, D and E. Now why? What happened? We know that this function is continuous. We checked for continuity right here. And so it meets. Let's take a look at what's happening. To try and save a little time, I've got a Desmos graph. So here's my Desmos graph, and we can see that right here at x equals 1, something's going on. And this graph, it's a little bit small, so what I want to think about is if we zoom in, right, if you were to zoom way in at this point, this is a linear function, this is that straight line, and this is a quadratic. It has this nice smooth curve. So even though these two things are continuous, where they meet right there, there is a bend. It's a sharp corner. If we were to zoom in a lot, you could see it a little bit better. So that's why this does not exist. It's not differentiable at that corner, at that point. It has an abrupt turn. That's it. We're not going to do 1B. You guys on your own are going to do 1A. So you have notes on the calendar. You can pull those notes up and use them. And good luck.